I will briefly talk about research progress in energy storage today, and I shall finish within about 15 minutes time. Talking about energy storage, the first question would be why? The primary reason for us to store energy is to match energy supply and demand, because these two are completely different things, and we have to match the supply and demand, which are often very different, and they differ very much in time and in quantity available. More importantly, nowadays we are having more and more low carbon renewable energy resources like solar power, like wind power, and all such energy resources are intermittent, thus making energy storage very necessary. And thirdly, energy storage can make our energy efficiency better. Energy storage is the bottleneck technology for many applications. It increases the operation time for devices like mobile phones and similar electronic devices, air drones, and electric vehicles. Energy storage also increases the fill factor significantly for renewable power stations like these wind and solar power stations. There are various ways to store energy. I'm going to quickly mention these energy storage methods in the next few slides. The first one is PHS, where energy is stored in the form of water's gravitational potential energy, MGH. And this method has been widely used by all the countries to balance electricity supply and demand because it responds very quickly with a relatively high return trip efficiency, around 80%. But it has problems too, including low energy storage density and geography limitations, because certainly for such device to work, we will have to have special geography. Another way to store energy is by pumped heat energy storage, where energy is stored via a reversible heat engine, which also works like a heat pump. So the charging process is realized by driving a heat pump, which converts electricity to heat. Then during discharging process, the heat pump works reversibly to a heat engine, which then converts heat back into electricity. Of course, in this kind of energy storage device, thermal energy storage is very important. Energy can also be stored within compressed air in the form of enthalpy. This way of storage has rather low thermodynamic efficiency. That is because energy would be needed during the expansion process for reheating. Simply because the adiabatic expansion process of air drops temperature significantly. So in order to increase the thermodynamic efficiency of a compressed air energy storage system, we will have to use thermal energy storage devices which store and recover waste heat from compression process, then get it rejected back into expansion process. Thermal energy storage TES is another way to store energy in the form of heat or thermal energy. It has three ways. It stores energy either via sensible heat, latent heat, or thermochemical heat. Sensible heat simply uses temperature variations to store energy, and latent heat uses phase change. And thermochemical thermal energy storage uses exo or endothermic chemical reactions to store a large amount of thermal energy. And TES is very important to several other energy storage methods like compressed air, where efficiency can only be improved by using TES. Also like pumped heat energy storage, PHES, the efficiency is highly dependent on the thermal energy storage system within. Hydrogen has been highly regarded as an excellent energy carrier because hydrogen offers extremely high energy storage density per kilo compared to conventional fuels. However, even liquid hydrogen, they do have a very low volumetric energy storage density, roughly about 25% of conventional fuels like gasoline or diesel. That means for the same amount of energy stored, hydrogen, even for liquid hydrogen, it'll have to be very big in volume compared to traditional fuels, which is not good for applications which has volume restrictions. Another big problem for both liquid hydrogen and the compressed hydrogen gas storage method is that both processes are very energy intensive. Liquid hydrogen needs a lot of energy for the cryogenic process, and the compressed hydrogen storage process needs a lot of compression work to be done. To overcome the volume issues of liquid hydrogen, people have come up with the idea of storing hydrogen in a chemical way, where hydrogen it gets locked within a special chemical. It could be a metal, alloy, or another chemical. In this way, hydrogen can be compressed into a smaller volume, even compared with liquid hydrogen. So in terms of volume, this is ideal. But if we are talking about weight, this is not ideal because most of the system mass would be the other supporting materials, components, because hydrogen has a very small atomic mass. So the weight percentage of the effective energy carrier hydrogen is rather low. Yeah. Another issue is that in order for the hydrogen to come out of this chemical system, heat would be required to be added into the system. Heat kind of just assists with this releasing process. So where does the heat come from? My group have been exploring the possibility of using TES to do this kind of thing. So TES simply just takes waste heat from the hydrogen storage process, which itself is a heat releasing chemical reaction. Then energy is safely stored within our TES. Then later on, when hydrogen is needed, we pump that waste heat stored within the TES system back into this chemical system, so that extra heat added will drive the hydrogen out of the system. So using this way, the thermodynamic efficiency of chemical hydrogen storage gets significantly improved. So TES actually becomes key for hydrogen storage then. By now, we have gone through many different energy storage methods. As we can see, almost all energy storage methods need excellent heat transfer to work efficiently. For example, compressed air energy storage does need TES and excellent heat transfer to increase the thermodynamic efficiency. Hydrogen storage, in its chemical way, doesn't also need TES and excellent heat transfer too. Even pumped heat energy storage itself is a kind of energy storage method between heat and work. So heat transfer is also important. So how do we enhance the heat transfer then? We could either use high thermal conductivity enhancers like metals, carbon materials, etc. Or we could also use materials which have high heat transfer contact area. For example, porous medium, which have many small pores inside, making a large surface area. So by combining these two ideas, we came up with this idea of metal foam. So metal foam looks like this. It has a lot of small pores inside, which gives metal foam a very high specific surface area, which is beneficial to heat transfer. And metal itself has a very high thermal conductivity, so that helps for heat transfer too. Metal foam is a kind of highly porous material, so the porosity can reach as high as 97%. The typical value is about 90%, 95, something like that. We'll have to model the geometry for the metal foam to investigate its heat transfer enhancement performance. I'm going to quickly show the results. These are the temperature and evolution as time goes during our energy storage process. We found that metal foam improves heat transfer significantly. For conduction, it is about 5 to 20 times, depending on the porosity and the pore size used for the metal foam. And low porosity is better because there is simply more metal material which has high thermal conductivity, and high pore density perform better because smaller pores here for high pore density produces higher specific surface area within, which is beneficial to heat transfer. And metal foam does suppress natural convection, which is not good for heat transfer, but because the heat conduction part has been enhanced by so many times that despite this suppression of natural convection, the metal foam still enhances heat transfer by roughly 3 to 10 times. We also investigated another kind of foam material, but it's not made of metal, it's made of carbon. So you can call it graphite or carbon foam because carbon is another material which has relatively high thermal conductivity like metal. If we can also make it porous to have a large surface area, then that is good for heat transfer too. These are the results. So effective thermal conductivity, the higher the better. So we see by adding EG means expanded graphite. So graphite has been made into a highly porous form. So when we add EG, the heat transfer had been significantly improved. The figure on the right hand side shows the same thing, but it just interprets heat transfer using a different parameter, delta T, the temperature difference, because the experiments were conducted under the condition of constant heat flux, which means the smaller the temperature difference, the better the heat transfer. Energy storage can also make our buildings more energy efficient. So typically, we can use a phase change material wallboard to moderate the temperature fluctuations in a building in order to reduce the energy consumption. In this regard, we have done a lot of research. We studied the effects of melting temperature values and their ranges. How do they affect the energy savings and thermal comfort of a building application? We studied the interior wallboard and also the exterior wallboard because they exhibit different characteristics. Also latent heat. Latent heat has to be large enough that a significant amount of, or I'd rather say a suitable amount of energy can be stored. But it doesn't have to be very high so that we have very strict restrictions onto the materials that we can use. Once the latent heat reaches a certain value, further increase of latent heat wouldn't have much of an improvement. Thermal conductivity also has effects on the wallboard, of course, because heat transfer is everything. Yeah. So thermal conductivity and generally needs to be enhanced for the heat transfer goes smoothly indoors and outdoors. But it can't be too high. If it's too high, it doesn't have that kind of insulation properties, so heat gets lost very quickly. Yeah, and also once the K value, thermal conductivity, reaches a certain value, further increase of K would not have much of an improvement for the in terms of the energy savings and the temperature fluctuations. That's pretty much everything that I want to cover today. And I have noticed that I have overrun the time. So thank you very much for your time. That's all from me.